Recently I have been asked how to assess whether a dataset is normally distributed or not. So actually you have several tools at your hands to check for normality. So what you can do is you could use a QQ plot, which is also called a normal probability plot, or use histograms. Both methods are visual methods in order to see whether there is a normal distribution or not. Then of course you could calculate some statistical parameters, for example the kurtosis, or you could apply, and of course you should apply, statistical tests, for example the Shapiro-Wilk test or the Lilliefors test. The problem with detection of normality is that you have to keep in mind that the number of data points in your dataset influences the results of your detection. So if you have enough data points, so for example more than 100 data points, then the detection of normality should be easy. If you have a smaller data set, then maybe you are running into troubles, and I just want to show this to you in a simple, very short experiment. We are creating two sets of data, one with 100 data points and another one with say 20 or 10 data points, and then compare the different approaches to detect normality. So for that purpose we just create a data matrix which has 2 columns and 100 rows. So if we look into the table editor, you see we have 2 columns, and now we just rename those columns in order to reflect the type of data which will be stored in the 2 columns. The first column will be filled with normally distributed data, and the second column will be filled with uniformly distributed data. So in order to do this, we just use this simple tool, creating the first column, column 1, filling it with normally distributed data using the function Gauss. And if you do this, then you see here we have here data points which are drawn from a normal distribution, and the second column, column 2, is filled by the function rand, and this function rand fills the column with uniformly distributed data between -1 and +1, so the interval is 2. Now we have here these data points, and now let's just check these 2 different distributions. First, I suggest that we create a histogram and select the columns. So what we have here, this is the histogram for the uniformly distributed data. Then we create another histogram just displaying the normally distributed data. So the first column shows up here and the second column shows up here, and you clearly see the difference between the normally and the uniformly distributed data. We can do the same. Let's just remove this and open another window, and using this window we just select the normal probability plot. And what you see here is this is the normal probability plot for uniform data, and another plot just shows the probability plot for the normally distributed data. And what you see is that for the uniformly distributed data you see this deviation here and here at the ends of the QQ plot, and in the case of the normally distributed data you see that the data points follow more or less the ideal line here. So which is an indication that this is normally distributed and this distribution is not a normal distribution. Of course we could just calculate the parameters, in our case the kurtosis. So for example you have here the kurtosis for the normally distributed data points, which is -0.3 approximately, and the p-value is 0.5. which means that the kurtosis comes close to a normal distribution. So if the p-value is above the critical threshold, then you have no reason to reject this null hypothesis, which means that indeed we have no reason to assume anything else but a normal distribution. On the other hand, if you're looking at the second column, which is the uniformly distributed data set, then you see that the p-value for the kurtosis is 0 or almost 0. And whenever the p-value is just below the critical limit, then you can conclude that the null hypothesis has to be rejected. And in our case, this means that the data set is not normally distributed. And of course, we can do this also with statistical tests. So let's just activate the statistical tests tool. What we do now is we just color the normally distributed data in red and the uniformly distributed data in blue. Then we apply the Shapiro-Wilk test, and you see the red ones, which is, you see it here, the red ones are the normally distributed data. The p-value is way above the critical limit of 0.05, which means that we cannot reject the null hypothesis. The null hypothesis is that the sample, which we just selected, the red ones, is part of a normal distribution. So we cannot reject it, so we assume that the red data points are normally distributed. In contrast, for the blue ones, which are the uniformly distributed data, you see that the p-value is below this critical limit, which is 0.05. And of course, we could do the same procedure with the Lilliefors test. And for the Lilliefors test, we get a result like this. So for the red, we get a p-value which is greater than 0.2, which is of course greater than the critical limit, 0.05. And for the blue ones, which are the uniformly distributed data, we get a p-value which is below 0.05. So all those methods which we just used showed us and indicated that we have normally distributed data in the first column and uniformly distributed data in the second column. Now let's just repeat this experiment using just 20 data points. So what we do is we just change our data matrix from 100 data points to say 20 data points, and then refill it with randomly selected data. So again, the first column will be the normally distributed data, and the second column will be the uniformly distributed data. And if you look into the data table, you see that we have now filled it with data points, and again the first column is normally distributed, the second is uniformly. And now let's just display all those plots we had before. These are the uniformly distributed QQ plots. This is the normally distributed QQ plot, and what you see is that actually you cannot recognize any difference. So maybe I should just remove the marks so that you can see the data points in neutral black color. And what you see is that here is the normally distributed data and here is the uniformly distributed data, and actually the deviations from the QQ plot are by no way significant. Let's also create the histograms for that. So what we just use is here the histograms for the columns, and we have here the histogram for the normally distributed data, and then let's also create the histogram for the uniformly distributed data. And again, what you see is that the difference is not that clear, so histograms won't help in this case. Now finally, let's just calculate the kurtosis. So what we have here is the kurtosis for the red data points. The p-value for it is 0.46, and here the p-value for the uniformly distributed data is 0.15. So you see, actually the p-value should be below the critical limit of 0.05, but in this case it's above, and the reason for that is that we have a small data set and the decision is not so clear anymore. And if you just apply statistical tests, so we just colored those in red and this one in blue, and then perform the Shapiro-Wilk test, then you see that the Shapiro-Wilk test for the blue data points just creates a p-value which is also above 0.05, which means actually the blue ones are the uniformly distributed data, but the Shapiro-Wilk test cannot detect that these are not normally distributed data. And the same for the Lilliefors test. So let's just start the Lilliefors test. And again, what you see here for the red data points, you get a p-value which is above 0.2, which indicates that it could be a normal distribution. But for the blue value, you have also a p-value of 0.2. So actually you clearly see that if you are reducing the size of your data set, say from 100 data points to approximately 20 data points, then you are already running into troubles simply for the fact that all those statistical methods to detect normal distributions are only good for larger data sets, but not for smaller ones. And what is the learning of that? Never be sure if you have just 10 data points or maybe 5 data points or maybe 15. Never believe that all those methods give you reliable answers. In order to detect a non-normality, you have to have at least 50 data points in your data set, and better would be, say, 100 or even more.